Alright, hello everyone. Welcome to my channel. We do educational material on this channel, and today is no exception. Today is the 291st day that we've been working with Dewey B. Larson's Reciprocal System of Theory. And the reciprocal system of theory is a theory of everything, or a system of theory, meaning that once you get the system, then you can plug it into any subject that you'd like. You have to kind of figure it out, and it's not easy. You need to be familiar with a lot of Larson's work before you can do that. But the basic idea behind Larson's system is that we live in a universe of motion. And this is a departure. Other people have posited that in the past, a few, but most people would say that the universe is made out of matter, or perhaps that the universe is made out of energy. Larson says that matter and energy are just two different varieties of motion, along with all of the other scientific quantities that we're familiar with, like acceleration and speed and electric current and electric charge and capacitance and resistance and force. These are all just different kinds of motion. And they are all similar in that they can be described exclusively in terms of space and time. For Larson, motion is the relationship between space and time. Relationship implies a ratio or a fraction, where you have either space or time as the numerator and time or space as the denominator. So for example, speed. The bicycle is moving 20 miles per hour. 20 miles of space in 1 hour of time. Space over time. Speed. Speed is space over time. Now, when you work these things out, you find out that energy is time over space. Matter is time to the third power over space to the third power. Force is time over space to the second power, whereas acceleration is space over time to the second power. Pressure is time over space to the fourth power. And so on and so forth. The reciprocal relationship that holds between space and time have no other significance other than they come together in motion. It's kind of like Larson uses the analogy of a box. Motion is a box. And if you have a box, you automatically have the inside of the box and the outside of the box. One is like time and the other is like space. And the box itself is the motion. And the basic... now, Larson kind of had an inkling of this stuff way back in the late 1920s, early 1930s, where he was trying to work out an equation for the interatomic distance between elements. And he basically just had this epiphany that what if you just assumed that space and time were reciprocals of each other? And he plugged it into the equation he was working out, and boom, the answer popped out. And so he was like, wow, that worked. So didn't think too much of it, I guess. But then he was working on another problem a few months later, and he was like, why don't you try that space and time are reciprocals of each other thing again? And the answer popped out again. And so he was like, take note. And he tried it again with another problem and got another answer. And so then he started doing a systematic study, but it took many years. He had a day job, so he was just working on it at night with his slide rule. And eventually, in the late 1950s, he put out his two fundamental postulates. The first of which is by far the most important, and that basically is that the universe is composed entirely of motion. At first he called it space-time. The universe is composed entirely of space-time. But he eventually turned that into motion. And motion is a relationship between space and time. So space and time both have their coordinate aspects, meaning that space and time both come in 3 dimensions. Coordinate, XYZ coordinates. And space and time both have their, they both progress. This refers to what Larson refers to as a scalar motion. That is a motion that has a magnitude but has no direction. A scalar motion is in time, like a clock. He calls it clock time and clock space. The clock is always getting later and later. It's moving later and later and later, but in no particular direction. And in space, you can envision this as dots on a balloon. You have a bunch of dots on a balloon, you blow up the balloon, all of the dots are moving away from each other, but in no specific direction. That was also observed by the Hubble telescope, that determined that all of the distant galaxies were moving away from each other. So that is what Larson calls clock space, or the progression of space. And then space and time also only come in discrete units. They are quantized, meaning that there is a minimum unit of space and a minimum unit of time. They are very small, but nonetheless, they are existent. So the minimum unit of space is about 4.56 times 10 to the minus 8 meters. So 1/20 millionth of a meter. And the natural unit of time is about 1.52 times 10 to the minus 16 seconds. So that is that means that of these units of time, you can fit 6.576 quadrillion of them in 1 second. So it's inconceivably brief. But say with the unit of space, it's a very small microscopic amount, but it is still very large compared to the size of an atom. So if you don't have a full unit of space or time, then you do not have space or time. So if you don't have a full unit of space, you don't have space. And by the reciprocal postulate and the general idea of the universe of motion, composed entirely of motion, if you don't have space, then you only have time. And if you don't have time, then you only have space. So those are really the 3 caveats that are listed in Larson's first postulate: coordinate space, coordinate time, clock space, clock time, and discrete units of space and time. Now, if you have exactly 1 unit of space in 1 unit of time, now remember, we already went through space over time is motion. 1 unit of space in 1 unit of time is what Larson calls unit speed, and that refers to the speed of light. The speed of light is unit speed, 1 unit of space and 1 unit of time. And the speed of light is really the null point, or the origin, or the ether, or the background, or the reference point of this universe. So if you have a universe of motion, you do not measure from zero. You measure from an already moving reference point. So you measure from the speed of light. That, you have to be able to accept that fact. In order to accept a universe of motion, you have to be able to accept the fact that motion precedes anything moving. And so motion is the most fundamental thing. So that's where you start your measurements from, is from something that's already moving. And Larson refers to that as the progression of the natural reference system, the speed of light outward in all directions at the speed of light. So that's where you make your measurements from, and that is also the null point, or the midpoint of this universe. So in Larson's system, half of the universe is actually moving faster than the speed of light, which Larson refers to as the cosmic sector. And half of the universe is moving slower than the speed of light, which we're familiar with. That's called the material sector, and that's where the scientists do all their observation and measuring. And that's why Einstein said that the speed of light is the maximum speed of the universe. So Einstein implicitly is saying that he doesn't understand anything about the cosmic sector. Now, what shores up that gap is that in Larson's system, there's a reciprocity. And so whatever is going on in the material sector, it is duplicated in the cosmic sector. The same thing is going on in the cosmic sector as the material sector, except that you have to invert the roles of space and time because of the reciprocal postulate. So in the material sector, you have coordinate space, 3 dimensions of space, and you have clock time. Time is always getting later and later and later. We're familiar with this. This is the sector that we make our observations from, the material sector. But in the cosmic sector, you have 3 dimensions of time and clock space. Space is always getting farther and farther and farther apart. And we looked at a paper the other day that was written by Dr. KVK Nehru, one of Larson's collaborators, who I believe is still living. Larson died back in 1990 at the age of 92. But I believe Nehru is still around. He's been following the reciprocal system and writing and contributing for many, many years. And along with Dr. Bruce Perrett, he put out something that is called RS2, the re-evaluation of the reciprocal system. So it's the reciprocal system with a few revisions. And Nehru was referring to the example of a quasar. A quasar is something that actually, it's in Larson's system, it is an exploding galaxy. And when that galaxy explodes, if the explosion is powerful enough, that explosion goes past the speed of light. So it crosses that boundary. It crosses that speed of light boundary from the material sector to the cosmic sector. And so Nehru looked at all of the different things that happen when you cross the boundary from one to the other, because you're trading in coordinate space for coordinate time, 3 dimensions of space for 3 dimensions of time. And you're trading in the progression of time for the progression of space. And so that has some consequences that are seen real life in the quasar and in some other astronomical figures as well, such as white dwarf stars and pulsars. That paper you may want to look at. It's an important paper. I did that for the last 4 episodes. Now for today's episode, we're looking at another of Dr. Nehru's papers that is called Consciousness, Motion, Space, and Time. And section 1 is called The Imaginary versus the Real. When we study occult truths and compare with the concepts of modern science, we should not lose sight of the fact that most of these concepts are actually assumptions that are not validated by facts. Black holes, curved space-time, the Big Bang, gravitational radiation, magnetic monopoles, the cosmic strings, only to mention a few, are all hypothetical objects conjured up in certain theories. A black hole, for example, implies infinite density and therefore cannot be physically real. Just to go back a few minutes here, one thing that I didn't mention is that with quasars, Dewey Larson actually predicted the existence of quasars before they were discovered. Okay, he predicted the existence of quasars a few years before they were discovered, and he predicted a list of about 14 of the characteristics that they would have when they were discovered. So it's not that Larson's theories are just hypothetical. They are indeed hypothetical, but they generally, especially in the case of the quasars, they prove to be predictive, and they eventually discover that he was right about what he said about quasars. Okay, now back to the black hole. For example, implies infinite density and therefore cannot be physically real. It is referred to as a singularity in the theory, something that the theorists recognize as a failure of the theory. However, instead of taking them as pointers to discard the theory in which they occur, the modern theorist continues to subscribe to these concepts. They double down on fantasy. Emotional attachment rather than adherence to fact becomes the driving point, the driving spirit, especially when the leading figures in the field patronize these unreal concepts. We tend to imagine that these concepts are valid. As another example, consider the general theory of relativity. Einstein takes gravitational field as identical to acceleration field. In the case of uniform fields, this does not give rise to any difficulty. However, in the case of non-uniform fields, like those of the planets, for example, no amount of mathematical jugglery can create an acceleration field that is identical to the geometry of the gravitational field. It is this geometrical difficulty that made Einstein adopt the idea that space is curved. Since he could not produce the required curved acceleration field from a Euclidean frame of reference, and could do so only from a non-Euclidean frame, Einstein assumed that space is curved. It has never been independently verified whether space could be curved, or how mass engenders this curvature. Okay, section 2 is called the general theory. The fact that we do not have a general theory, the fact is that we do not have a general theory of physics. A general theory is one that explains all physical phenomena from the atomic to the astronomical, encompassing them in a single cogent structure, and does not contain ad hoc assumptions. The fact that we do not have a single theory, but only a collection of individual theories, goes to show that the basic concepts of these individual theories are not right. Therefore, attempts to understand the occult truths from the points of view of these concepts, which are only provisional working hypotheses, cannot lead us to truth, but only speculations unlimited. The emergence of the first truly general theory, namely the reciprocal system of theory created by Dewey B. Larson, should be of immense interest to all the seekers of truth. The conclusions of the reciprocal system are factually verified in all the domains of physics and astronomy. It must be noted that there cannot be more than one correct general theory. I have to think about that. I don't know that I agree with that, but it seems like all the general theories that I study, they're all correct, and they're all saying the same thing, but they're using different language. So it's just a nuance. I think I agree with his statement in principle, but in practice, different people kind of use different languages to express the same thing. Imagine a single sentence of coded message. Creating a physical theory of limited applicability is like finding the key to the code. If the message is short, it is quite possible to come up with more than one unique key, resulting in alternative meanings to the code. Now, the creation of a general theory is like finding the key to a very long sentence, say an entire book in code. The probability of the existence of an alternative key that makes the entire book still intelligible would be zero. Thus, we can see that once we have a valid general theory, then it would be the general theory. Now, an example I would give for that is, say you're trying to find the key to a very long message in code. Well, Dewey Larson finds the key to this message, in code, into this this whole book. He comes up with the key, and he's got the English code for the book. But somebody else could come along and decode it in a different language, decode it in French. And that would be a different code. They're saying the same thing, but they're speaking in different languages. So I think I think Nehru's probably right about what he's saying, but that, he's kind of not looking at, different languages that will say the same thing, but in a different language. If you speak in physics, you might say one thing, but if you speak in astronomy, you might say another thing. If you speak in geometry, you might say another thing. And if you speak in linguistics, you might say another thing still. So I still think that it's very useful to do comparative theories of everything. Many of the people that I study, they have theories of everything, and I believe that they're correct, but they're expressing the same thing in different languages. If you can come up with a theory of everything about music, but it's not going to be in the same language as your theory of everything about physics, but it will have the same fundamental, bases. And I think that's the beauty of comparative theory of everything, is that you can have great insights by comparing the different things that they're saying, and realize and recognize and figure out how they are saying the same thing but in different languages. Okay, we will stop it right there and tomorrow we will resume on this paper, Consciousness, Mass, Matter, Space, and Time, with section 3 that is called The New Paradigm. And thanks for tuning in today. Have a great day.